I am hediye from Graduate School of Engineering, Kyoto University. It's my great pleasure to be able to present this paper in this excellent conference. I would like to also apologize that I'm not able to be in this conference in person and visit the beautiful Turkey again. The presentation that I would like to give is related to advanced imaging technology. My talk will have two parts. The first part will be related to using the synchrotron radiation in cell microbiology. The main topic of my talk is analytical imaging and its application in cell microbiology. In this talk, we present the experimental investigation using two very important techniques, synchrotron radiation, XRF, and ZAFs. These are two methods that can analyze extremely low level of trace elements in the biological tissues. We also later introduce a complementary approach to the investigation of artwork, which is in a non-invasive and non-destructive and can be applied in situ. Most of what I'm going to talk about is presented in the book that I published almost 10 years ago, application of synchrotron radiation in and especially the microbeams in biology and medicine. Here, I would like to briefly explain one of our typical experiment. Here is the cell, and there is a very small amount of metallic elements, which usually are very toxic, incorporated in these cells. The aim of this study is to investigate changes in the densities, distribution, and chemical state of intracellular elements simultaneously by using synchrotron radiation, X-ray fluorescence spectroscopy, imaging techniques, and microspectroscopic imaging technique. The background of this talk is that we're using synchrotron radiation from the synchrotron devices, accelerators that I will explain later. We usually get this kind of spectra which shows the concentration of elements in a single cell. Very, very low level of elements in a single cell. Here, by using several mathematical steps that I'm going to not to go into details here, we will get some more information about this spectra. And then we use these data and we developed our own imaging programs to visualize these distribution of these elements. I also would like to add one point that there is a big difference in what we are doing using this kind of imaging compared with a electron microscope or a scanning electron microscope or a transmission electron microscope. Through electron microscopy, we can see the shapes of the cells and the shape of how the cell looks like. Here we compare two cells, one which as a control cell, and the second one on the right side is a phagocytosed cell. This means that we added a small amount of very small amount of metallic elements in the cell. And then, for example, this is also a transmission electron microscope, a very high level of details. We can see how the metallic elements are incorporated in the cell. But to do this, we need to take slices of the cell, which means the original shape of the cell is changed. These are also other transmission electron microscopic images that I showed just now. Here I would like to talk about the experimental setup. These experiments that I'm going to talk about, or I was just talking, we use the Spring 8. This is an accelerator this is the image of the accelerator, which is about 1,500 meter in circumference, and then this is the inside view of the beam lines. So you can imagine a huge experimental system that we use to produce extremely thin micro beam of a very high intensity X-ray. So these are different parts of the setup, and this is the beam line that we use and the different parts of the beam lines, and then I'll show it's how it's being, and now I'm going to show the images. So these are the final image, or not exactly the final, one step before the final image of the trace element in a single cell. And then we use conventional smoothing methods to make the images more acceptable, more easy to see. And here we can also see the relation between different elements at a single cell. Why we are interested in this kind of experiments? Because usually the trace elements, especially the toxic metallic elements like vanadium, they have a highly negative influence on a single cell, and in many cases it ends into the death of the cells. We can imagine that if these materials are incorporated into the brain nerves, then the cell dies, and then it ends, or it causes several neuro diseases such as Alzheimer and Parkinson and the other diseases more or less with the same causality, the same effects. Here is a very, very important part of our experiment, part of our research, which we could distinguish the chemical state of extremely low level material trace elements in a single cell, and the density of, for example, here you can see that the density of iron in its doubly or triply triply charged state is less than 0.004 microgram per liter. Very, very small amount. The second part of my talk is also related to this the digitization and using digital technology, analytical digital technology to first of all do imaging of the material, and second to use these images for analysis. But the second part of my talk will be completely different from the cell microbiology. It's more or less the same spectroscopic but visible in the visible region to try to see what kind of composition or constitutional element the material has. I'm not going to talk in more details because of the lack of time. I would like you to try to find some of our published papers. These are the equipments that we designed in our laboratory, and we constructed the whole thing, but the mechanical part, the optical design, and also all the necessary imaging programs for running these equipments. This research, we had three main parts or three main aim for imaging and also using these images. Here I would like to emphasize that when you do the imaging in extremely high resolution of very big objects, like for example an artwork or a big part of the human skin with extremely high resolution, you will get a file that is about a few gigabytes. So to be able to do this kind of research, we also had to develop the big data files, which are about a few gigabytes, and the biggest one is about 100 gigabytes. So our research has three parts. The first part is doing extremely high resolution and scanning technology, and the second is how to use these images for analysis, and the last part is how to display these big files. These are different equipments that were developed in our laboratory, and now used in more than 10 different countries in Europe, in United States, in China, and other Asian countries, and in more than 80 universities around Japan and around the world. I would like to emphasize on the spectroscopic part of this technique, these equipments. Here we have an artwork or an image which consists of different material and produces different color. We use multispectral imaging. Multispectral imaging is the imaging that we usually use and we see around us is a three-color image, but here we use more colors or more spectral bands to produce exactly as detail as possible of the spectroscopic curves of the material which has been used in these objects. Here I also would like to add one very important point. The spectral reflectance that maybe some of the audience here use in their laboratories are beams of a few millimeter. So when you have a spectra, the spectra looks like this. But when we use our equipment, we can we can estimate a spectral reflectance which is at a single pixel, which can be about a few micrometer. So we call this system, or the way that we use this system, a mesoscope. Mesoscope is not a microscope, because microscopes are very high definition, but they can only see very small areas. But here we have the images which can be at a very, very large area. For example, 2 meters by 8 meters. So it's not a microscope, but we can see big, very big images and go into details like a microscope. So this is my presentation. I would like to thank you very much. I have one more video clips. If the time permits us, I would like to show this video clip of our very recent work that is shown in Japanese mass media. Thank you very much for your attention.